Math 1332, Chapter 2, Set Theory, Section 2.2, Subsets and Set Operations, Video 7, Number of Subsets of a Set. Now, I could do like a lot of professors do and just tell you, here's the formula to count the number of subsets a set has, but that's no fun. I want to see if I can get you to see it before I say it. How? By looking for a pattern. To establish a pattern, let's start with some pretty small sets. See if we can list all the subsets and count how many there are. And if you notice, these sets just get progressively larger in terms of their cardinality. Recall that cardinality is the number of elements in a set. The empty set, whose cardinality is 0, a set containing A only, whose cardinality is 1. Oh, by the way, a set containing one element is sometimes called a singleton set. A set containing 2 elements, A and B, 3 elements, A, B, and C, 4 elements, A, B, C, and D. And let's see how far we can push this until a pattern emerges. Now notice I said subsets and not proper, which means we can include the set itself. Since subsets are allowed to be equal, proper subsets are not. Let's start with the empty set. Any subsets? Well, let's get something out of the way right now. The empty set is a subset of every set. That was stated in video, I think video 4. So we can go ahead and go to every one of these and list the empty set. Get that out of the way. Now, how are we going to list the rest of them? Well, first off, this is the only subset of the empty set, so the number of subsets here is 1. Moving to the next set. A set containing only A. The empty set is a subset, but so is A itself, or the set containing A, I should say. Remember, every set is a subset of itself, not a proper subset, but a subset. And these are the only possible subsets I can make here, so that would be 2. I'm going to erase the empty sets, and I have my reasons. Oh, they're going to be put back, don't worry. But let's think about how we could build subsets of the next one. Notice that the set containing A is a subset of the set containing B. That means that all of these subsets should also be over here. Empty set and the set containing A. But because all of these subsets came from over here, none of them contain B. Subsets over here can contain B. So I can make more subsets by taking these and putting a B with them. For example, if I take the empty set and add the letter B to it, I get the set containing B. Or if I take the set containing A only and add B to it, I get the set containing A and B. So essentially, I took all the subsets from over here and what's the best way to say this? I don't want to say I added B, okay, we'll just say add B. Can't think of a better word. Include B as an element. The correct word is union, but I'm trying not to use that word right now. All right, so we took all the subsets that didn't have a B and gave them a B to make new subsets that couldn't have been over here because there was no B over there. 1, 2, 3, 4. So basically, every set over here got to show up twice, once without the new letter, once with the new letter. Guess what I'm going to do over here? Same thing. The set containing A and B is a subset of the set containing A, B, and C, which means every subset over here will also be a subset over here. Empty set, set containing A, set containing B, set containing A and B. But because these subsets were subsets over here, none of them could have the letter C, and now they can. So I'm going to do the same thing I did over there. I'm going to take all of these sets and I'm going to add C to them because now C is an option. If I add C to the empty set, I get the set containing only C. If I add C to this set, I get the set containing A and B. A and C. If I add C to this set, I get the set containing B and C. And if I add C to this set, I get the set containing A, B, and C. The entire set. Which means now I have 4 twice, which is 8. So by taking all the subsets from the previous smaller set, writing them and then writing them again with the new element, the number of subsets doubled. So how many subsets do you think this guy will have? Look at the pattern of the number of subsets. 1, 2, 4, 8, 16. I'm going to list them all. It's going to be kind of fast. First, let's write down all the ones that don't have D. Empty set, A, B, AB, C, AC, BC, ABC. So those are all the subsets over here that don't have a D. Now to get all of them that do, I just have to add D to all of these. If I give D to the empty set, I get the set containing D. If I give it to the set containing A, I get the set containing A and D. The next one would be the set containing B and D, and then A, B, and D. Remember, all I'm doing is I'm giving D to all of these. C and D, A, C, and D, B, C, and D, and then finally A, B, C, and D. So we had the original 8, and then another 8 for a total of 16. So think of clear patterns emerging down here. 1, double to get 2, double to get 4, double to get 8, double to get 16. And that's a nice pattern going from one cardinality to the next. Remember, cardinality is the number of elements. 0 elements, 1 element, 2, 3, 4, but what if there were 10 elements? What if I went all the way to A, B, C, D, E, F, G, H, I, J, and said how many subsets? Well, you can see this is going to get out of control, but I would know how to get there. Just keep doubling until I hit the 10th one. By the way, the answer would be 1,024. It's a lot of subsets, and I don't have time to write them all. But how do I know it's going to be 1,024? Because instead of looking at a pattern from one number of subsets to the next, which is called a recursive pattern or an implicit pattern, I would rather look for a pattern that connects the cardinality. When I have 0 elements, 1 subset. When I have 1 element, 2 subsets. When I have 2 elements, 4 subsets. When I have 3 elements, 8 subsets. When I have 4 elements, 16 subsets. Because if I can find that connection, then I don't have to build my way up to 10 elements. I can just say take the number 10 and do this to it. Now you may recognize 1, 2, 4, 8, and 16 as a certain other pattern, and you may not. But it's just powers of 2. 16 is 2 to the 4th power. 8 is 2 to the 3rd power. 4 is 2 to the 2nd power. 2 is 2 to the 1st power. And for algebraic reasons I'm not going to get into, 1 is 2 to the 0 power. And by rewriting all of those numbers as powers of 2, I'm exposing the cardinalities of the original set. In other words, this set had 4 elements, there's a 4. This set had 3 elements, there's a 3. This set had 2 elements, there's the 2. 1 element, there's the 1. Even 0 elements, there's the 0. So we can draw a conclusion. Now, this isn't a proof. This is evidence of a formula. The proof would require something a little bit more rigorous, but we'll save that for a more advanced math class and just claim the following. The number of subsets of A is 2 to a power, but the power matches the cardinality. Remember, cardinality is asking the question, what's the number of elements in this set 4? What's the number of elements in this set 3, etc., etc., etc. So we can represent this exponent by saying the cardinality of the set. Now this may look a little intimidating, but this is simply saying count how many numbers are in the, how many elements are in the set. Use that as the power of the 2. So for example, if A has 10 elements, which is the same as saying n of A is equal to 10, cardinality of A is 10, then A has 2 to the 10th, and if you multiply 2 times 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 2, you get 1,024 subsets. And there we go. We now have a formula that says, how many subsets do you have? Count the number of elements raised to that power. Now before we wrap up this video, I want to do one more real quick formula, and it's a formula for the number of proper subsets. Remember the difference between subsets and proper subsets? They're practically the same, however, with proper subsets, they also cannot be equal. And I wish I hadn't erased these, but oh well, it's already there. I can do it on these. If I wanted the number of proper subsets, I would do the exact same thing, except I would have to exclude the set itself. So for example, for this one, I would have to exclude that one and say that there are 3 and not 4. On this one, I would have to exclude that one and say there is 1 and not 2. And on this one, I would have to throw that one out. Remember, proper says they can't be equal, and now there is 0 instead of 1. But if you notice, all I did is throw away one set, the set itself, because proper says you can't be equal. So what does that mean? That means that the formula for the number of proper subsets is the same as the formula for proper subsets, but you subtract 1. The number of proper subsets of A is, let's open this up, 2 to the cardinality power, but after you calculate that, then you have to subtract 1. Now be careful. I'm not saying subtract 1 from the number that's in the power. I'm saying do the power, and then after you've done it, subtract 1. So for example, if A has 8 elements, then A has 2 to the 8th power minus 1. Well, 2 to the 8th power is 256. But 256 minus 1 is 255. Proper subsets. It's all the subsets, but you have to throw away the original set itself. Hence the minus 1. So it's a fairly straightforward calculation. If the symbols are throwing you off, just remember, count the number of elements, multiply the number 2 that many times, and then subtract 1, if it's proper.